In this video, you will learn about how to use the GCF method of polynomials in order to factor. Let me know if you have any questions in the comments below. And don't forget to subscribe so you don't miss out on future videos. Let's jump right in. This is called the greatest common factor because it's simply the largest factor that all of the terms share, stressing all of the terms share. So you can ask yourself, what does every term have in common whenever you're working on a GCF problem? So in order to factor using the GCF method, it's practically the distributive property, but in reverse. So after you're done, you could just do the distributive property and see if you get the original expression. So when you do the GCF method, you can ask yourself, when I pull out the GCF from every single term, what is left? Let's jump right into an example. So here are two specific examples side by side. Notice the one on the left versus the one on the right are exactly the same, except the one on the left is +7 and the one on the right says +6. So if we take a look at the expression written on the left-hand side, if you're asked to factor using the greatest common factor method, first of all, it's important to note that there are 3 terms, and you can tell how many terms there are because they are separated by plus and minus signs. So for each of these 3 terms, is there something that every single term has in common? Well, notice that this has 2 x's, this middle term has 1 x, and the 7 term has no x's at all. So we can't pull an x from every single term. If we look at just the coefficients or the numbers, this 2 and this 20, it's looking good because those are both divisible by 2. But the problem is this 7 now adds a problem. There is no number that the 2, the 20, and the 7 have in common. In other words, there's no number that they are all divisible by. So in this particular case, it's not that this expression is not factorable in general, but if the directions were to say factor using the GCF method, this is not factorable, using the GCF method. But if the directions say to factor, that's what I'll talk about later. Notice this is a quadratic expression. This might be factorable using other tools in our toolkit. In general, maybe this might not be factorable at all, but we're talking about GCF. So in this particular case, there is no greatest common factor with all 3 terms. As opposed to if we look at the expression on the right-hand side, now that we have this 6 here, it helps us out because now we see that the 2, the -20, and the 6 are all divisible by 2. So the greatest common factor is 2. Now, technically, whether you pull out a +2 or a -2 doesn't really matter. But if we pull out a +2, again, as we discussed before, it's pretty much the distributive property in the reverse. So you can ask yourself, if you pull out a 2, what's left when we divide by 2 in every single term? Or you can look at, as I said before, the reverse distributive property. So 2 times what gives me 2x squared, x squared. 2 times what gives me the middle term, -20x, a -10x, so I'm going to write -10x. And then 2 times what gives me a +6, a +3. So I'm going to write a +3. So this is not a factor completely problem. If this was, then we have to see if this guy here was factorable as well. But again, if we're just looking at the greatest common factor, we can just leave it in this form. So using the greatest common factor method, you can pull out a 2. Now this is a really simple, but really highly important, honestly, tool to note, is because later on when we're going to factor quadratics, it really makes sense whether that leading coefficient is a +1 or a number that's not equal to 1. So if in this example, you know how to factor out the greatest common factor, now you are focusing on a quadratic where the leading coefficient is 1. And that makes life a lot simpler because you're going to actually use a shortcut method. So if you didn't understand a word I just said, you can skip down into the quadratic section to know exactly what I'm talking about. So if we have a really funky expression like this, and we're trying to factor out using the greatest common factor, again, you have to ask yourself, what does every single term have in common? So again, it's important to note there are 3 terms again here because we can see that all of these 3 guys are separated by plus and minus signs. So you have to look at each single term, and let's actually go ahead and look at just the numerical values. The 20, 15, and the 35, those are all divisible by 5. So we're going to pull out a 5 from each of those terms. Now notice in this first term, there are 8 x's, the second term there are 5 x's, and the third term there are 3 x's. So there are at least 3 x's that we can pull out from every single term. Here's a 2 x's in this expression, 2 x's in this expression, and 3 y's, I meant to say, not x values, 3 y's in the third expression. So there are at least 2 y's that we can pull out from each term. Last but not least, there are 2 z's in the first term, and there's 1 z in each of the last 2 terms. So there are at least 1 z that we can pull out from every single term. So once you figure out what the greatest common factor is, by the way, if this was like a quiz or a test, if you have no idea what to do next, just writing this here will give you points, because your teacher is looking for points to award you, not to take away. So even if you just figured out the greatest common factor correctly, you will definitely get some points. So never leave anything blank. You should never hand in a quiz or a test blank. Okay, so now we figured out what the greatest common factor is. So it's time to do the reverse distributive property. We're going to write the greatest common factor on the outside, and we're going to do it step by step. So this GCF times what gives me the first term? Well, 5 times 4 gives me 20. X to the third times what gives me x to the 8th, x to the 5th. So remember, we are adding exponents here. 3 plus 5 gives me 8. Y squared times 1 is y squared. So actually, we don't need to add any more y's here. And z times what gives me z squared. So we need another z here, right? Because z to the first times z to the first is z to the second. So again, we're just adding exponents. Now this GCF times what is going to give me this middle term. So 5 times what gives me 15, a positive 3. So I'm going to write a plus 3. X to the third times what gives me x to the 5th, x squared. So again, 3 plus 2 gives me 5. Now we already have a y squared, so I don't have to add any more y's. And there's already a z there, so I don't have to add any more z's. So we're done. Last but not least, we have to figure out what does this GCF times what gives me that last term. And just make note that that 35 term is negative. So 5 times what gives me a negative 35, a negative 7. So I'm going to write a minus 7. There's already an x to the third in that term, so we don't have to add any more x's. We do need to add a y though, because y squared times y is y to the third. And actually, we already have a z in that term, so we don't have to add any more z's. So again, look at it as the reverse distributive property. So if we were asked to factor using the greatest common factor method, we are done. I hope this video helped you use the GCF method to factor polynomials. If you like this video, make sure to subscribe to my channel right now. That way you don't miss out on my future videos like this one. Just click on the subscribe button below.